This is a 25-year-old semi-truck, and right now it sells for more money than a brand new equivalent. It's a 1999 Peterbilt 379. No computers, no modern emissions filters, no laptops required. Just fuel, iron, and a wrench. Truckers will pay a premium for this because it will run 1,000,000 miles, a family heirloom made of iron and chrome. It represents the peak of American engineering before a 50-year war between physics and politics changed everything. The engine didn't die because the engineering failed. It died because the boardrooms and the courthouses won. And to understand how we got here, you have to go back to before the EPA even existed. Back in the 1950s and 1960s, the only law that mattered was engineering. Nobody at Cummins, Detroit, or Caterpillar was thinking about microscopic nitrogen oxide. They had exactly one job: build an iron block that made more power, ran longer, and burned less fuel than the last one. And the platforms coming out of that era were legends before they even had time to become legends. The Cummins NH220, the Detroit 671, the Cat 1673. These weren't complicated machines. They were iron blocks, mechanical fuel pumps, camshafts, and push rods. A guy with a decent set of hand tools and a factory manual could pull one apart on the side of a dirt road and put it back together well enough to get home. Thermal efficiency: squeeze the air, inject the fuel, burn it completely, dump the heat fast, turn the crank. No compromises, no chemistry sets. The engine that burned its fuel cleanest made the most power and burned the least diesel. It was that simple. And every manufacturer in the industry built to that same principle. Detroit Diesel took that principle and gave it a sound. The two-stroke 671 and the 8V92, the Screaming Jimmies, ran a fundamentally different combustion cycle than everything else on the road. Where a standard four-stroke engine fires every other revolution, a Detroit two-stroke fired every single revolution. Every downstroke was a power stroke. The result was a high RPM wail that you could hear from a quarter mile out, and a power density that nothing else could touch for the money. Operators rebuilt them on the highway with basic tools. Trucking companies ran them past 500,000 miles on the original rotating assembly. They refused to die. Black smoke rolling out of the stacks wasn't a problem back then. It was proof of concept. A loaded Mack ENDT 675 pulling a long grade with a dark cloud trailing behind it meant the driver knew exactly where to put his foot and how much fuel that grade demanded. The smoke was the visual signature of an engine working at the edge of its thermal limit, and to every driver who understood diesel, it was the most honest thing a machine could show you. That world started cracking in the early 1950s, and the crack started in Los Angeles. Dr. Ari Hagensmit at Caltech had spent years proving that the brown haze sitting over the LA basin wasn't coming from a single factory or a power plant. It was a photochemical smog, unburned hydrocarbons and nitrogen oxides reacting in the sunlight. The cars and trucks running through Southern California were cooking the air. California moved first. By 1966, the state had the nation's first tailpipe emission standards. By 1967, the California Air Resources Board was chartered. The regulatory apparatus was built and loaded before Washington ever got involved. Then on December 2, 1970, Nixon signed the Clean Air Act into law and stood up the Environmental Protection Agency. William Ruckelshaus became the first administrator. His mandate was simple and unforgiving. The era of unrestricted exhaust was over. The first federal heavy-duty emissions targets landed on the industry's desk, and while the early standards weren't specifically targeting diesels, the framework was there. The mechanism was in place. All it needed was time and political will. California wasn't waiting on Washington. CARB moved ahead of the federal EPA at almost every step, setting stricter standards and forcing manufacturers into a nightmare situation. Engineer one engine for California, a different tune for the other 49 states. Tool rulebooks, 2 certification processes, 1 production line. The suits started doing the math and didn't like the answer. The first real hardware casualty came out of that math. To control visible smoke under the new opacity standards, engineers bolted an aneroid valve onto the mechanical injection pump. The idea was straightforward enough: sense turbo boost pressure, physically bypass fuel pressure back to the tank until the turbo spooled up, prevent the black puff on acceleration. Clean test, clean number, satisfied regulator. What it actually did was cut a hole in the throttle response right when a driver needed it most. A loaded rig pulling out of a truck stop onto a 2-lane highway, driver puts his foot down expecting immediate torque, and instead gets a stumble, a hesitation, a dead spot, while the turbo catches up. Operators started calling it the puff limiter. and most of them pulled it off with a crescent wrench before the end of the first week. The EPA had just built its first safety hazard in the name of clean air, and the guys running the iron knew it immediately. As NOx limits tightened toward the 1985 standards, a thermal fix required to hit the numbers was bigger cooling. Air-to-air aftercooling started replacing jacket water systems. The charge air coolers were massive, 36 inches wide, multiple rows deep, bolted in front of the radiator. To fit that hardware under a hood, you needed a bigger hood. Peterbilt retired the 359 and brought out the 379 in 1987, longer and wider, specifically to swallow the new cooling packages. Kenworth stretched the W900 for the same reason. The EPA didn't just change what was under the hood, it changed the shape of the hood itself. But while the engineers were widening the trucks to handle the heat, the EPA was sharpening the blade for the most iconic sound in trucking history. By the early 1980s, the black smoke wasn't a badge anymore, it was a federal violation. The EPA's particulate standards were tightening fast, and the engine that had defined American trucking for 40 years was about to get a death sentence written in the Federal Register. To understand why the two-stroke Detroit couldn't survive, you have to understand something about its design that nobody talked about when it was making everybody money. The Screaming Jimmy had a flaw baked into its DNA, a fundamental characteristic of the way it breathed that made it a legend in the 1960s and a federal criminal by the 1990s. It wasn't that the engine wore out, it was that the very thing that made it great had become a violation of federal law. And once you see it, you can't unsee it. Because the two-stroke had to scavenge spent exhaust gases out of the cylinder while simultaneously pulling fresh air in, both happening at the same time through ports cut directly into the cylinder wall. A gear-driven Roots blower had to force pressurized air through those ports to push the exhaust out of the top valves. Fast, loud, brutally efficient on power density. Here's the problem the EPA exposed. Those same cylinder wall ports the air blew through were sitting right next to oiled cylinder walls and piston rings. Every time the blower forced air through that cylinder, it picked up microscopic oil droplets off the walls and swept them straight into the combustion chamber. Some of it burned, a lot of it didn't. It came out of the stack as particulate matter, the dense black smoke that was the Screaming Jimmy's calling card. You couldn't tune that out. You couldn't filter it downstream. It wasn't a carburation problem or a timing problem. It was baked into the breathing cycle. The architecture itself was the violation, and no amount of tighter tolerances or better injectors was going to change that physics. Detroit tried anyway. When the EPA set the 1991 particulate limit at the 0.25 grams per brake horsepower hour and then dropped it again to 0.10 for 1994, the math closed out. The two-stroke highway diesel was done. Detroit ended on-highway production of the two-stroke in 1995. An architecture that had powered American freight since before World War II was regulated out of existence, not because it wore out, but because the EPA drew a line it couldn't legally cross. Roger Penske had seen the wall coming years earlier. When GM was ready to exit Detroit diesel in 1988, the company held roughly 3% of the heavy-duty truck engine market. 3%. That's not a struggling business, that's a dying one. Most operators in that position would have sold the tooling, locked the doors, and walked away clean. Penske walked in instead, took majority ownership, and made one of the sharpest calls in American trucking history. He looked at the same regulatory storm that was killing the two-stroke and decided to build straight into it. The Series 60 was his weapon, a four-stroke inline-six with full electronic control designed into the block from the ground up, not bolted on as an afterthought. Where every other manufacturer was retrofitting electronics onto mechanical architecture and praying the combination held together, the Series 60 was built to live in the electronic world. The DDEC system gave fleet managers real-time data on fuel burn, idle time, and driver throttle habits. The EPA wanted tighter control over combustion. Detroit handed them the most controlled combustion event in the industry and built a competitive advantage out of it. By 1993, Detroit diesel held somewhere between 26 and 33% of the market. 3% to a third of the industry in 5 years. The Series 60 didn't just survive the regulations, it used them as a weapon to gut the competition. While Detroit was rebuilding, International Harvester was bleeding out. IH entered the 1980s as one of the most complete industrial companies in America. Trucks, engines, farm equipment, construction iron. Then a brutal 172-day UAW strike in 1979 and 1980 drained the company, while the farm crisis of the early 1980s collapsed their core agricultural revenue almost overnight. In 1986, what was left renamed itself Navistar International, The IH badge was gone. The legacy debt stayed. The wound never healed, and it explains every desperate, corner-cutting decision Navistar makes for the next 3 decades, including the catastrophic MaxxForce gamble that nearly finishes the job the farm crisis started. For the operators who had built careers on two-stroke iron, none of the corporate restructuring meant anything, except that the engine they knew was gone. Guys who could time a 671 by ear, who could diagnose a bad injector by the color of the smoke, had to start over. The EPA didn't put those guys out of business directly, it just changed the ground under their feet. The 1991 NOx standard forced the next transformation. To hit 5.0 grams per brake horsepower hour, fuel delivery had to be controlled with a precision that mechanical injection pumps physically couldn't deliver. The timing window was measured in microseconds. The fuel quantity was measured in fractions of a cubic millimeter. Springs and gears and centrifugal governors couldn't operate at that resolution, so the computers took over. CAT introduced the 3406E in 1993, running a mechanically actuated, electronically controlled unit injector, an MEUI system, where the camshaft still drove the mechanical pressure, but a solenoid controlled by the ECM fired the actual injection event. Cummins brought the N14 Select to market with a similar approach, keeping the Bulletproof 855 cubic inch block architecture, but handing the fuel map to an electronic controller. Detroit's DDEC system on the Series 60 went even further, giving fleet managers data on idle time, driver throttle habits, and fuel consumption in real time. The engine stopped being just a machine. It became a managed asset. Operators loved the power and economy. The 3406E and the Series 60 were genuinely excellent engines. More power, better fuel efficiency, longer overhaul intervals than anything that came before. But the guy who used to carry his whole toolbox in a milk crate behind the seat was now carrying a laptop he didn't know how to use. By the mid-1990s, CAT's electronic technician software and Cummins Insight had locked the fuel map behind factory access codes. A $5 coolant temp sensor could throw a fault code that shut the truck down on the side of the road, and the nearest authorized dealer with the right software was 3 weeks out. The EPA's NOx mandate hadn't just changed the engine, it had quietly handed ownership of the machine from the operator to the dealership network. The iron was still fundamentally right, the engines were reliable, they were powerful, and the operators who learned the new systems respected them. The Series 60 and the 3406E were genuine triumphs of engineering. While the manufacturers were celebrating their sales numbers and data control, the EPA was setting a trap that would change the industry's relationship with the government forever. What the EPA's ambient air monitoring network eventually found stopped the room. Every major diesel engine manufacturer in America had been running a double life inside their ECMs, and the way they pulled it off was straightforward enough that it took years for anyone outside the industry to spot it. The cheat worked like this. The EPA certified engines using a standardized laboratory test cycle, a controlled dynamometer run that simulated urban stop-and-go driving. The manufacturers knew exactly what the test looked like. Steady throttle inputs, predictable load curves, specific RPM ranges. So the ECM software was written to recognize those conditions and switch into a clean fuel map. Retarded injection timing, reduced combustion temperatures, NOx numbers that satisfy the regulators, and got the certificate signed. The moment that truck merged onto a highway under a real load, the software recognized the change in operating conditions and switched back to the real tune. Injection timing advanced back to where it needed to be for power and fuel economy. NOx output climbed to as much as 3 times the certified limit. The operators got the truck they paid for. The EPA got spreadsheets that looked clean. Nobody asked too many questions until the ambient air monitoring data stopped matching the certification numbers. On October 22, 1998, Attorney General Janet Reno and EPA Administrator Carol Browner stood in front of cameras in Washington and called it what it was. According to the EPA, 1.3 million heavy-duty diesel engines had been sold with illegal defeat devices. The agency estimated those trucks were putting out excess NOx equivalent to the combined emissions of 65 million passenger cars annually. The civil penalty totaled $83.4 million, the largest Clean Air Act fine ever issued at that point. But the money wasn't the punishment that mattered. Buried deep in the legal text of the consent decree was the actual hammer. The industry had been working toward a 2004 compliance deadline for the next round of NOx standards. Standards that required a fundamental shift in combustion architecture, specifically the mass implementation of exhaust gas recirculation. The engineers had until January 2004 to figure it out. That was already a tight window for a technology that had never been proven at scale in a commercial heavy-duty application. The consent decree pulled that deadline forward to October 1, 2002. 15 months of R&D time gone. The engineers who needed 4 years got less than 2. Every major manufacturer's internal engineering staff warned management the same thing. EGR technology isn't ready. The coolers will crack. The soot will destroy the turbos. The fuel economy penalty will be severe. Get us more time. Management signed the decree anyway. The alternative was federal prosecution. The operators who understood what was coming didn't wait around. Between 1999 and the third quarter of 2002, they bought every pre-mandate truck they could finance. The 6NZ Cat, the N14 Cummins Select Plus, the Series 60 DDEC4 in 12.7 and 14-liter configurations. Dealerships ran out of inventory. The pre-buy wasn't nostalgia, it was triage. These operators had read the engineering warnings, and they were stocked up on the last engines that were built without a government-mandated timer on the reliability clock. October 2002 arrived, the engineers did the best they could with the time they had, and the iron paid the price. The EPA wanted a cleaner tailpipe. To get it, they handed engineers a mandate that went directly against the fundamental physics of how a diesel engine makes power. They weren't asking for a compromise. They were asking engineers to violate the basic laws of thermodynamics, and every engineer in every engine lab in America who looked at the EGR requirement saw the same thing. You can't fight thermodynamics. The iron always loses. The guys who signed the decree weren't the ones who'd have to build it. The engineers who had to build it already knew what was coming, but the clock was running, so they built it anyway. EGR sounds simple on paper. Take a portion of the exhaust gas coming out of the engine, cool it down, route it back into the intake manifold, mix it with fresh air. By diluting the oxygen charge with inert exhaust gas, peak combustion temperatures drop. Lower temperatures mean less NOx. The EPA signed the certificates. Ask any driver who ran a first-generation EGR truck what it felt like. There was a flatness to it, a hesitation at the top of the power band where the engine used to pull hardest. Most drivers didn't know the EGR cooler was already cracking from the inside. The service bulletins hadn't caught up to the field reality. By the time the white smoke showed up, the damage was done. Here's why it happened. Diesel combustion lives and dies on one thing: a dense, cold, oxygen-rich air charge meeting precisely timed high-pressure fuel. That combustion produces a complete burn. Maximum energy extracted, maximum heat dumped out the exhaust stack and away from the rotating assembly. EGR takes that cold oxygen-rich air charge and replaces a chunk of it with hot oxygen-depleted exhaust gas, loaded with soot particles and trace sulfur compounds. The combustion quality drops immediately. The burn becomes less complete. More soot forms inside the cylinder instead of out of the tailpipe. The engine retains more heat instead of expelling it. And because the burn is less efficient, the engine needs more fuel to produce the same horsepower. Field data from early EGR era consistently showed a 10 to 15% fuel consumption penalty just to maintain the same pulling power. The EPA was counting the grams of NOx leaving the tailpipe. Nobody at the agency was counting the extra gallons of diesel going into the tank. The hardware that EGR forced onto early emissions era diesel engines made everything worse. Because the soot-laden exhaust had to be cooled before it re-entered the intake, manufacturers bolted on EGR coolers, liquid-cooled heat exchangers running between the exhaust manifold and the intake tract. These coolers experienced brutal thermal cycling, with hot exhaust gases pushing past 1,000 degrees Fahrenheit on one side and engine coolant running around 200 degrees on the other. The extreme temperature delta eventually caused the internal tubing to fatigue and crack. Under heavy load, high-pressure exhaust gas would force its way into the cooling system, overpressurizing it and blowing coolant out the overflow. When the engine was shut off, residual coolant pressure forced liquid into the EGR stream, where it pooled in the intake tract. Operators saw unexplained coolant loss and white smoke upon startup. If ignored, this $1,200 cooler failure would dump a cylinder full of coolant, triggering a hydrostatic lock that resulted in a bent rod or cracked block, turning a minor leak into a $15,000 or $30,000 engine rebuild. The turbocharger situation was just as bad. To force exhaust gas back into a pressurized intake manifold, the engine required exhaust back pressure that a fixed geometry turbo couldn't provide. Engineers solved this with variable geometry turbochargers, VGTs, units with sliding internal vanes that could restrict exhaust flow on command to create the necessary pressure differential. While the vanes worked beautifully in clean air, the EGR-heavy environment created immense amounts of particulate matter. Soot and carbon built up in the vane tracks and baked solid, freezing the mechanism and turning a precision instrument into a grit-locked paperweight. A turbocharger that previously lasted the entire life cycle of the engine was suddenly downgraded to a highly predictable wear item, adding a $4,000 repair bill to the maintenance schedule far earlier than operators ever expected. Mechanisms failed so frequently that repair shops began stocking them the way they used to stock fuel filters. Caterpillar refused to go down that road without a fight. Their engineering department had rejected cooled EGR as fundamentally destructive to long-term reliability, and for the 2004 mandate they built a different path: ACERT, Advanced Combustion Emissions Reduction Technology. Twin turbos in a compound sequential arrangement, variable valve actuation, multiple injection events per cycle, a diesel oxidation catalyst in the exhaust stream. It was genuinely clever engineering. The ACERT C15 had serious pulling power, and the twin-turbo setup managed heat better than a single VGT in soot-heavy conditions. But clever isn't the same as proven. Chronic injector failures and actuator malfunctions piled up fast. Fleets started tracking downtime by the day. In June of 2008, they made it official. Caterpillar was exiting the North American on-highway truck engine market entirely. After 70 years, you could frame that as a cold business decision. Mining, marine, and power generation were paying top dollar for cat iron without the same regulatory stranglehold. The numbers made sense on paper, but the engineers who'd built the 3406E and the C15-6NZ knew what it really was. Caterpillar didn't leave because they couldn't build an engine that met the 2010 standards. They left because they weren't willing to build a bad one and put their name on it. When you've spent decades building iron that runs 1,000,000 miles, you don't bolt a compromised emission system onto it and call it progress. You walk. More than 1.5 million drivers were running cat-powered trucks on American highways when that announcement came down. Every one of them watched the residual value of their equipment start moving in the wrong direction that afternoon. While Caterpillar was walking away, Navistar was doubling down on a strategy that their own engineers had been warning was a suicide mission. The internal emails were already frantic. The test data wasn't closing. The coolers were failing at a fraction of their required service life, and the people running the numbers knew it. Management knew it too, and sold the trucks anyway. The full picture didn't come out until a high-stakes civil trial, and what came out in that courtroom was one of the most damning statements ever made under oath about how a major American engine manufacturer brought a product to market. Daniel Ustian at Navistar watched Caterpillar leave and made the opposite decision. Where Cat retreated, Ustian doubled down. His competitors, Cummins, Detroit, Volvo, were all moving towards selective catalytic reduction for the 2010 NOx standard of 0.20 grams per brake horsepower hour. SCR treated the NOx after it left the engine, using a urea-based fluid injected into the exhaust stream to break the nitrogen oxides down into nitrogen and water. It worked. It let the engine run its optimal combustion tune again. The fuel economy penalty from the EGR era largely disappeared. Ustian decided the EF fluid was a liability. He told his engineers to push EGR rates to 30% and build a compliant engine without the secondary fluid system. His engineers told him it wasn't physically possible at commercial scale. He overruled them, and the engineering leadership that pushed back was systematically gutted. The MaxxForce 13 went to market on emissions credits, while the actual 0.20 NOx EGR only engine remained uncertifiable. Internal emails, later surfaced in litigation, showed Navistar executives knew the EGR coolers in the MaxxForce design were failing at less than 20% of their required service life. The company sold the trucks anyway. The warranty costs tell the story. Navistar's baseline warranty expense ran around $300 million per year. By 2011, it hit $399 million. By 2012, $455 million. It peaked at $637 million in 2013. Over 6 years, the MaxxForce disaster cost Navistar more than $1.1 billion in excess warranty claims alone. That number came out during a landmark civil trial, Milan Supply Chain Solutions versus Navistar, where a senior executive testified under oath that the company didn't test before selling the MaxxForce engines to the public. The jury awarded $30.8 million in damages. Ustian was eventually barred by a federal court from serving as an officer or director of any publicly traded company. In July 2012, Navistar quietly abandoned the EGR-only strategy and began incorporating the same SCR technology that they had spent years publicly ridiculing. The MaxxForce disaster was a warning shot that the old way of fighting regulations was dead. As Navistar surrendered, the industry entered a new phase. one where the engine finally breathed again, but the computer took total control. The SCR era was supposed to be the peace treaty. Let the engine breathe clean again. Treat the NOx downstream in the exhaust pipe, everybody moves on. And in pure engineering terms, it worked better than EGR ever did. The fuel economy came back. The soot stopped grinding through the rotating assembly. The engines made honest power again. What the EPA added to enforce it, it nearly broke the independent operator for good. DEF, diesel exhaust fluid, freezes at 12 degrees Fahrenheit. And when a DEF line freezes or a quality sensor misfires, the engine management system doesn't ask questions. It initiates a derate sequence, cuts power to a fraction of rated output, flashes warnings across the dash, and begins a countdown to a 5-mile-per-hour crawl. The mandate required manufacturers to program that response in. The intent was compliance enforcement. The reality was a $200 urea quality sensor stranding a $180,000 truck in a construction zone with 44,000 pounds of freight on the trailer. Operators started calling it planned obsolescence by algorithm. The block wasn't failing. The heads were fine. The injectors were holding pressure. The computer had simply decided the chemistry wasn't right and removed the operator's ability to make a decision about their own equipment on the side of the highway. The right to repair fight that had been brewing since the mid-1990s software lockouts finally had a crisis visible enough to reach Congress. California didn't wait for that fight to resolve. CARB pushed its drayage rules so far ahead of federal standards that trucks fully legal in 48 other states became ineligible to work the Port of Long Beach. Operators running pre-2010 equipment in Wyoming or Texas had clean-running, properly maintained trucks that couldn't legally cross into California to pick up freight at the nation's busiest port complex. The glider kit industry grew directly out of that pressure. Fitzgerald Glider Kits in Tennessee industrialized the Loophole. New cab, new chassis, rebuilt pre-emissions engine. Cheaper than a new truck and legally immune to software derates. At peak production, over 3,500 glider units per year were rolling out of their facilities. When the EPA finally tested these trucks at the National Vehicle and Fuel Emissions Laboratory, the results were damning. Official EPA laboratory data showed the pre-emissions engine in those new glider chassis emitted NOx at 43 times the rate of a properly built 2014 or 2015 truck, and particulate matter at 55 times the rate. The EPA moved to cap production under the Obama-era Phase 2 rules. The IRS assessed a $268 million in unpaid excise taxes against Fitzgerald's operations. By 2019, Peterbilt had halted glider kit sales, and Freightliner followed right behind them. The loophole closed. Then, in January 2024, the DOJ, EPA, and CARB announced a $1.675 billion civil penalty against Cummins, the largest Clean Air Act fine ever secured in American history, and the second largest environmental penalty of any kind ever issued. It was the 1998 playbook all over again, updated for the SCR era. Defeat device software embedded in ECMs across roughly a million Ram, 2500, and 3500 pickup trucks written to survive the test cycle and cheat the real world. 25 years later, different truck, same fundamental problem. The mandate was written faster than the physics could follow, and the engineers found a way to survive it. The cheat wasn't a rogue decision in one company's ECM department. It was an industry-wide response to targets the engineers already knew were incompatible with real-world operation. CARB's 2036 zero-emission mandate is now on the books. New diesel truck sales in California done by law in exactly 10 years. The Iron Heart is being asked to retire on a government timeline. Meanwhile, a clean 1999 Peterbilt 379 with a 6NZ under the hood sells for $80,000 to $100,000 at auction. That price isn't nostalgia. It's the market's final vote on which era of engineering actually won. The cost of cleaner air was the extinction of the most reliable engines this country ever built, and the permanent fracture of trust between the men who run the iron and the institutions that regulate it. The 6NZ Cat, the N14 Cummins, the Series 60 Detroit. Those engines weren't preserved because operators are sentimental. They were preserved because the physics were right and the mandates were wrong.